So what are some of the challenges chemists may have with their MS data? Most of the time you're looking for just M plus or M plus H or M plus sodium. And if it's there, you don't give your data a second thought. But it's not always that simple. The parent ion may not actually be the largest peak. Your product may not even readily ionize, and it may not be detected, or it may decompose before it's even reached the detector. If you're working with structural isomers, they will be virtually impossible to distinguish based purely on the parent peak alone. Your compound may look pure on NMR and LC, but that doesn't mean that there aren't other ions in there. And it's tempting to write off all of the peaks in your mass spectra as being fragments of your product. But if you aren't sure how your molecule is fragmenting, these could be contaminants from your reaction or even from the machine itself. Searching for literature on mass spec data can often be quite futile, as a lot of the time you're lucky to even find the confirmatory ions recorded in the experimental data. Now, I have noticed it is gradually becoming more common to include mass spectra in the supporting information, but the peaks aren't always labeled, they're not always assigned, and this in itself can be difficult to make sense of. And lastly, trying to generate fragmentation pathways for your compound by hand is time-consuming, difficult, and carries a degree of bias to it. I will admit that I've wasted a good part of an afternoon, more than once, trying to justify the presence of a peak or lack of a parent ion in my mass spectra by cutting my molecule up, trying to find a structure with the right mass, lose a methyl group here, gain a methanol adduct, put a potassium ion on. And unless you're very knowledgeable about fragmentation, this can be quite time-consuming, and it's an often fruitless and not really scientific way of looking at your spectrum as you're trying to make your data match your desired results. Luckily, MS Fragmenter can get around some of these problems. It's developed entirely in-house, and it fragments your compound using known fragmentation patterns from the scientific literature, which you can customize yourself depending on the type of molecule or ionization technique that your laboratory works with. It only takes a few seconds to generate thousands of fragments, far faster than any chemist could do so, and it displays them in a format that is easy to navigate, and you can isolate branches of interest relatively quickly, and if needed, generate a report in a fraction of the time it would take to do it by hand. And what's particularly useful is if you're working with a new compound or even a new class of compound, the software is able to reveal fragmentations and rearrangements that you may not be aware of, which not only helps you understand what is going on inside your mass spectrometer, but possibly also during your reactions and degradation studies as well. Because the software generates fragments based on existing fragmentation pathways, it's not trying to create a fragment of a particular mass. And by doing this, you're eliminating the element of human bias when trying to manually generate your own fragments. So if you have access to ACDLabs MS Workbook Suite, this comes with MS Fragmenter. You can also purchase the software on its own. So here is an overview of what the software looks like. From Chem Sketch, we can draw or import the molecule, and then it's just a simple button press, and the software will generate several fragmentation pathways. Shown here, a list of all of the ions it has calculated, a display window with all of the structures, and a tree demonstrating the actual fragmentation pathways themselves. There are several ways to narrow down the pathways to focus on fragments of interest, and I'll show you that during the demonstration. However, the most relevant way to do this is by comparing the fragmentation results directly to your MS data. Here I have generated a fragmentation pathway based on this compound, thiophyl, and a list of the ions that have a list of fragment ions that have been generated. And because I'm able to compare this to my spectra using MS Fragmenter, I can actually limit the number of ions that it has displayed to only include ones that are directly relevant to my compound. You can also use the assign fragments function in Spectra's processor to generate fragments from your compound and assign them directly to the spectrum automatically. And lastly, generating fragmentation reports is just a matter of clicking a few buttons. Here, I've displayed the fragmentation branch for this diltiazem derivative here to this smaller compound here. And it can automatically generate a scheme complete with masses, fragmentation losses, chemical formulae, all in a matter of seconds. You can also include a list of fragmentation parameters and a list of ions and show several branching pathways simultaneously. Okay, so that's more or less it for the introduction. So I'm now going to move on to the demo of the software itself. Okay. So this is MS Fragmenter. Right now, all of the windows are empty as we haven't selected our target molecule just yet. The layout is designed to be easy to navigate. And as you can see, there are only a few buttons at the top. Before I can demonstrate the function of these though, we need to get a structure. So let's go into Chem Sketch. So in Chem Sketch, we can draw out our compound or import one from an existing file. ACDLabs software is fully compatible with ChemDraw, Marvin Sketch, ISIS Sketch. So if you've already got a compound you wish to investigate, you can just copy and paste it directly in. Just to speed things up a bit, I'm actually going to select a molecule from the ACDLabs dictionary. So we'll go with etiphenin, shown here. Because the MS Fragmenter program is open, the contextual buttons at the bottom of the screen have changed to show functions that are relevant to MS Fragmenter software. So clicking Fragmenter will simply take us back into the fragmentation program. However, the one we're interested in now is generate fragments. So what this is doing now is using the predefined options, which I will show to you later. It is now breaking apart every conceivable combination for this molecule. I've selected it to potentially break any and all bonds. And I'll go into a little more detail about that later in this webinar. But in the meantime, let's see what it has come up with. Okay, so the layout of the fragmentation is shown in this window up here, the fragmentation graph. In the lower left, we have a list of the fragment ions. And on the right, we have the structure display window. So I'm just going to expand out the fragmentation graph first. So the fragmentation graph shows the parent ion here and all of the fragmentation routes below. Each level represents the number of fragmentations, 1, 2, 3, and so on. And within each level, ions of the same mass are grouped together. So for example, this box shows a list of 17 compounds with a mass of 286 that can be generated in 1, 2, 3 steps from the parent ion. A child ion, which has the same mass, either shows an ionization or an isomerization or a rearrangement. As there are quite a lot of ions here, there are a few ways to narrow it down. If we click the minus sign on each box, this will hide all of the subsequent fragmentations of this compound. So if there's pathways that you're not interested in, then you can narrow them down just by remove them like so. If I go up here and I click collapse all, that will minimize every single box. And then you can then expand them one at a time, following particular branches that you're interested in. If you click expand all, this will then reopen every single box and show every pathway again. Depending on your preference, you can have the window left aligned, center aligned, or right aligned. I prefer to have it on left aligned, so I'll just turn that back to where it was. If you would like to see the chemical formula alongside the ion, you can switch to tree view. This converts the graph into a list format, and it can be navigated the same way, showing the number of steps to get to each fragmentation, and it also includes the chemical formula next to the name. I personally prefer the smart graph layout, so I'll switch back to that. So let me talk about the display window. So if I select this box, in the display window, you will see that it gives it displays the structures for this particular fragmentation path. It shows the parent ion, each of the fragments, and ultimately at the bottom it will be the last box in that chain. If you select a box which still has child ions coming from it, they will be displayed below. You can also see the nominal, isotopic, and average masses, the chemical formula, the fragment that has been lost, and the number of ions in this particular grouping with the same mass. So for example, in this particular chain, you can see that our parent ion loses water, then it loses a carbonyl, it then undergoes several rearrangements, and then loses the entire aromatic ring section of the molecule. You can also cycle through ions of the same mass just by clicking on these arrows here. If you change to a compound that is part of a different fragmentation pathway, then this will also change all of the preceding and following fragments. As you can see, the ones beneath it are also changing. If you want to simplify the display window and the fragmentation graph, then you can select compact view. What this does is condense all of the radical and ionization isomers and their rearrangements to a single representative compound. So for example, two different tautomers will normally have both forms shown, but with compact view on, only one will be displayed. And if there are different radical positions, then it will condense all of these into a single view. And as you can see, it has narrowed down the view to show only one representative compound of each particular mass. And as you saw, it took a little while to run the first time. However, once it's run once, you can switch back to detailed view and back to compact view relatively quickly. Okay, so if there is a mass that you're interested in, you can use the ion list to isolate a particular fragment. If you check the boxes next to that mass, it will eliminate everything in the fragmentation graph. Actually, let's switch back to detailed view. It will eliminate everything in the fragmentation graph which is not in some way related to those particular ions. So as you can see, it's showing all of the branches leading to and from the masses at 230 and 229. You can also search for a particular fragment by structure. If I go back into Chem Sketch and I load a particular fragment in, just load this in, and let me get rid of this. So if you load in a particular fragment, and if you click search at the bottom here, you can then use this to search for that particular fragment within MS Fragmenter. And as you can see, it has isolated it here. Now I've still got these masses selected. Let me expand that out again. There we go. And now it's showing the entire fragmentation pathway to this particular fragment that I was able to search for. Okay, so in this particular example, using etiphenin as a starting parent ion, we generated fragments from a drawn structure in Chem Sketch. And as you can see, there are several ways to change the layout and narrow down the structures displayed. But if you have a mass spectrum, you will likely want to compare the predicted fragments to your experimental results. So let's go into Spectra's processor. And I'm just going to load an example file. Okay, so here we have a thiocarbohydrazide derivative and the mass spectra for it. Now, if I right-click on the structure display box and I click Run MS Fragmenter, it will fragment this compound like before, and we can directly compare our results to the spectrum once it has finished loading. Okay, so we have our fragments like before, and our display window, and our list of ions. So what it has done is generate every possible fragmentation for this compound, but that doesn't necessarily mean that that is what is appearing in our spectrum. So what I can do is click filter by spectrum, and in this case we can use high resolution. We can define our accuracy tolerance. I will just leave it on 0.5 Daltons. Okay, so what it's doing now is it's comparing the generated list of ions that are present in the mass spectrum to what was generated here. And if there isn't a spectrum open, it will alert you and tell you to abort the search. Now it can take a little while to do this. Yeah. So as I said, it really depends on how you've chosen the molecule to be fragmented. And as I have chosen every possible permutation, it will just simply go through and break the molecule apart in every conceivable way. But some of these ions may not actually be observable in the mass spectrum itself. There we go. So as you can see, what it has done is tick the relevant ion boxes, similar to what we did before manually, but in this time, it's found these relevant masses in our mass spectrum. And it has just simply narrowed down the list in the fragmentation pathway to only include ones that are present in the mass spectrum. So we can be fairly confident that these ions are real possibilities in terms of what might actually be happening in the mass spectrometer. Now, as a side note, if you are familiar with the MS Workbook Suite, and you have used the auto assign function. This is effectively performing the same function as MS Fragmenter, except that it is generating the list and assigning them entirely within the processor shell itself. So what this will do is, again, generate the list of ions, narrow them down based on what is actually in the spectrum, and it will then assign each fragment based on its mass. Okay, so here we've generated a list of ions, and you can see as I scroll through them, it's highlighting the relevant one in the mass spectrum. So if you have access to MS Fragmenter, you also have access to this piece of software, and the function assign automatically within Spectrus. If you just have Spectrus processor, but not MS Fragmenter, you will not have this function. And as you can see here, it has assigned 98% of the spectrum, so that's generally pretty good. Another particular advantage of this assignment this assignment record is that if you have two isomers, you can run the auto assign function on both of them, and if one of them fits the mass spectrum better through fragments, then you can get a much better idea of which isomer is more likely within your particular spectrum. Okay, so I've talked a lot about how to do the actual fragmentation, but I haven't talked about the fragmentation options themselves. So from either Chem Sketch or from MS Fragmenter, you can select options, and these are the user settings that you can edit in order to determine how it is going to fragment your molecule. So you can choose the ionization type, positive or negative. And if you're using positive, then there are several different options you can choose. Atmospheric pressure ionization, chemical ionization, fast atom bombardment, and you can choose what adducts are going to be present. There are certain options that need to be included for multi-components, like whether you remove charges beforehand or any small components such as sodium ions. And then you've got common reactions, dystonic ions formation, what bonds you want to cleave. I've just put it on all bonds. And if you're generating a very large number of fragments, you might want to narrow them down either by limiting the number of fragments or by increasing the minimum mass value. I've just put them to give me the maximum number of fragmentations. There are also some specific fragmentation options such as heterolytic and homolytic cleavage, hydrogen rearrangement, skeletal rearrangements. Now, I won't go into details about what all of these options mean. However, if you want to know more about them, then you can just simply click on the help button shown here, and this will open the Fragmenters help section, and it gives a much more detailed description of what each of these options are referring to and what turning that option on or off will do. Okay, so that's there if you need it. So the last thing I am going to show you today is reporting. So let me just choose a fragment. Let's say I'm interested to know, how this fragment is formed. So first of all, you need to have your reaction displayed in this window shown here by clicking on the appropriate box. And then if you go to the report button, this will bring up the create report window. So here you can select what to include in the report, like the MZ values, the fragment formulas, labels, and fragmentation options. You can also include a page title, user information, any comments you wish to include, and the date. So The main choice, though, is what fragmentation you want to show. Clicking current fragment only will display only the current structure. Clicking on fragmentation pathway will create a upside down branching tree starting from the parent ion to all compounds selected with the same mass, whereas fragmentation branch will show a linear path from the parent ion to the ion that's been selected. So this is the one I've selected at the moment, so let's just see how that looks. So obviously if you have more compounds, then it will take longer to generate, but as you can see, it's generated a single pathway complete with the appropriate ionizations, fragmentations, masses, formula, and how this mass relates to the starting material, to the parent ion. Now I'll go back into something I forgot to show. If I go back into Chem Sketch, you also have your list of fragmentation options, list of MZ values, and of course, you also have your name, date, and the name of the report. If I go back into Fragmenter, I'm going to pick a shorter pathway for this one. And if I select this time the fragmentation pathway, then what this will do is, rather than generating a single linear path, it will create a branching pathway showing all, showing all fragmentations from this particular ion towards a particular ion of a certain mass, and how each of those ions are generated. Okay, so that's it for the software demonstration. So in short, if you want to use the software to fragment a particular compound quickly, it will do that. And unlike manual fragmentation, it's based on actual scientific literature, existing pathways, and depending on what machine you use, what ionization techniques you use, you can customize the fragmentation settings yourself. It's very easy to narrow down the generated pathway either by directly comparing it to your spectra or by using the auto-assign function within Spectra's processor itself. As you see, you can also manually narrow it down either by searching for a particular ion, searching for a particular structure, or just following a pathway of interest by manually clicking through the boxes that have been displayed. And lastly, generating reports, either by showing the single path, the single branch of the fragmentation, or by showing a branching fragmentation tree. Either of these can be done relatively quickly just using the report function.